All right, let's get started. And today we are going to talk about transactions. I've already very quickly introduced the topic in the previous lecture. Now we're going to see the details. So we are going to define what a transaction is in a moment. Know already that the components in a database system that are important for transaction processing, they are mostly located in the storage manager. And here in particular, we are focusing on the so-called transaction manager component. But in a way, all of the other components in the storage manager, they contribute towards enabling database systems to give all the guarantees about transactions that we will discuss in more detail in the following. Now, the relevant chapter in Ramakrishna and Gerke, that is chapter number 18. And first of all, we're going to define what a transaction is. So a transaction is generally a sequence of updates and queries that is somewhat semantically connected. And you can tell the database management system that they are connected. We will see corresponding commands, for instance, in Postgres later. And once the database system knows that certain steps belong to the same transaction, then it ensures a certain guarantees. For instance, it makes sure that either all of the steps associated with a transaction are executed, or that none of those steps is executed. So you cannot have situations in which only part of your transaction was executed, but the other part was not executed. So one example domain in which you definitely need transactions, that is banking. And let's start with a very simple example for a transaction. Let's simply say we want to transfer $50 from the account of Alice to the account of Bob. So that means we essentially have two writing steps, two updates to the database. First of all, we need to subtract $50 from the account of Alice. And then we need to add $50 to the account of Bob. And both of those steps are semantically related. So obviously, you do not want to execute only one of those two steps, because otherwise either Bob has not as much money as one should expect, or otherwise both people have more money than they should. So those two steps are semantically linked, and you would typically represent them as one transaction to the database system. Now, for instance, in Postgres, you can start a transaction with the begin command. Then all of the following commands will be considered as part of that transaction. And then once you have finished all the steps from your transaction, then you can write the commit command. Then the database management system knows that this transaction has been finished. It now should be executed. So everything between begin and end is part of the same transaction. Database management systems, they make the so-called ACID guarantees when it comes to transaction processing. And this acronym abbreviates 4 important properties in the context of transaction processing. The A, for instance, stands for atomicity. And that means we either execute all of the steps in a transaction, or we execute none of them. There's C for consistency. And here that essentially means that the transaction leaves the database in a consistent state. So all of the constraints on your data will be satisfied. Otherwise, the transaction is aborted. Now, typically, you have multiple users executing transactions concurrently on the same database. And then it becomes important to shield one user from the actions of another user. And this is what we mean by isolation. So we make sure that those transactions from different users don't interleave in a bad manner. Finally, we have durability. And that means that once a database system has told you that a transaction has executed, at that point, it guarantees that the updates by the transaction are never lost, And that includes situations where, for instance, your server suddenly crashes, maybe there's a power outage or something like that, but the database makes sure that it can recover all the updates by a transaction. So this was a short overview. Now in the following, we're gonna see those important properties in a little bit more detail, starting with atomicity. And as I have said before, atomicity generally means that we execute either all of the steps in a transaction or we execute none of them. Now, first of all, why would a transaction not fully execute? There's various reasons, actually. I mean, one reason, for instance, is that the system suddenly crashes while it is in the process of executing a transaction. Maybe, for instance, there's a software bug, or maybe there's a power failure. Another possibility is that a transaction does not execute because it tries to make an update that violates some of the integrity constraints. For instance, it violates a foreign key constraint connecting two tables. Also, you have an explicit command to aborted transactions. For instance, people might use that with a condition around it. So for instance, if certain conditions are not satisfied, then a transaction is aborted. In Postgres, the corresponding command is called a rollback. Now, internally, the database management systems, of course, they don't execute the entire transaction in one atomic step, but they execute one step after the other one. So that means if there's really a problem and the transaction suddenly is interrupted, then internally the database management system actually has to execute a couple of cleanup steps in order to make sure that no partial effects of the transaction are represented in the database. Consistency is about guaranteeing that all integrity constraints on the database are satisfied. So those constraints include, for instance, primary key constraints. So transactions cannot insert any duplicate values in terms of the primary key columns. We have foreign key constraints which connect different tables together. And you can also define a more complex constraints. And in general, if a transaction tries to make an update that threatens to violate some of those constraints, then a database management system will abort the transaction. And there's a little caveat that comes with this term. There's also consistency in the context of distributed systems. You might already have taken corresponding courses. So please be aware that the consistency in the database sense is a little bit different from the consistency in the distributed system sense. So here consistency means that all the constraints on the database are satisfied. Now, isolation means that we shield users from the action of other users, which is important because different users typically execute transactions concurrently. For instance, if you have a banking application, then you would typically have many clients that are trying to transfer money or do other things with their accounts concurrently. So the database system needs to be able to handle that. Now, we could, of course, imagine maybe we just keep things simple and we just execute one transaction after the other one. The reason why we are not doing this is performance. For instance, imagine that one transaction is currently waiting to load data from hard disk. So in general, that only takes maybe a couple of milliseconds, but in the context of data processing, that is actually a long time. So instead of waiting until the data has loaded from hard disk and keeping the processor idle until then, what we could do is that instead we fit in between a step from a different transaction which executes on data that is currently already in main memory. So the access will be very fast. And doing that can often increase efficiency. So that motivates us to try to overlap operations from different transactions instead of executing them serially, meaning executing one transaction after the other one. Now, even if we internally interleave the steps of multiple transactions, we don't want users to become aware of that. Because as a user, if you're writing a transaction, things become very, very complex if you need to take into account that other users might change the data that you're working on while your transaction is executing. That would become very complex code. So in order to keep things simple, we want to simulate to users that their transaction executes as the only one in the system currently. And that guarantee is called isolation. Finally, we have durability. And that means essentially after the database system has told you that your transaction has committed, meaning the execution has finished and everything related to this transaction has been done. At that point, the database system guarantees you that the updates of the transaction will be persistent in the database state. And that holds even if we have those crashes, for instance, due to power failure. No matter, the database system must guarantee that it can recover all the effects of the transaction before it tells you that the transaction has committed. So this guarantee is about keeping your data safe. All right, so those are the 4 guarantees that database systems typically make when it comes to transaction processing, the ACID acronym. In the following, we're going to discuss those properties in more detail. Except for consistency, consistency is a fairly natural to implement. That just means that the database system checks all the constraints and aborts transactions if they don't satisfy them. So we're not going to discuss that in more detail, but we are going to discuss about isolation now in the coming slide deck. And in the later lectures, we will discuss about atomicity and durability. So in the following, we're going to first of all discuss about the isolation guarantee, where we shield users from the actions of other users. All right. And I have a little demo for showing the effects of isolation. Let me quickly prepare that. All right. Okay. And now you should be able to see my screen. All right. So now I want to give you a little demonstration for the effects of isolation. So if you have installed Postgres on your machine, then you can also try that demo yourself. So generally, we need to log into the database simulating 2 different users. So here I have opened 2 different terminals. And now I have already created a database called banking. So this is what we will use for this example. All right, so now I'm logging into the database in both of those terminals. All right, and you see that worked. So now we are connected twice to the same database. All right, so for this example, let's create a simple table representing the account balance of different users. So we have a name and we have an amount of type integer. All right, and now this table has been created, so I see it here And of course, you also see it here because here we are connecting to the same database. Now let's insert a couple of example values into that database. Let's say that Bob, let's say that Bob has $100, and let's also give $100 to Alice. All right. So if we show the content of the table, then now both of them have $100, and here it's going to be the same thing. All right. Okay. So now in the following, we are going to start a transaction, and we're going to transfer $50 from Bob to Alice. So first of all, we are starting the transaction. So here we are marking to the database system the point where the transaction begins. And the following commands will be considered as part of that transaction. All right. So now the database system has notified us that the transaction has started. And as first part of that transaction, we reduce the amount of dollars on the account of Bob. So we said amount equal to amount minus $50, where the name equals to Bob. All right. And now here in the left terminal on the screen, let's call that user number 1. So user number 1 has now executed a first change on the database and reduced the dollar amount of Bob by $50. So if user 1 runs the corresponding query showing the content of the table, then that change is already reflected. So you see here, the dollar amount of Bob has been reduced by $50. Now on the other side, if I go to the other user, to user number 2 here in the right-hand terminal on the screen, if that user currently runs select the content from the accounts table, then as you see here, nothing has changed. And this is isolation in action. So on the left-hand side, we have already started changing the database, and we can see those changes ourselves. But on the right-hand side, a different user doesn't currently see those changes at all. Let's continue. So user number 1 now adds the $50 to the amount to the account of Alice. All right. And again, if you see what happened here, we see that Alice now has $50 more than before. Again, on the other side, for the user number 2, nothing has changed so far. Both of them still have $100. I mean, that makes sense already at this point. It could be that perhaps the transaction of user number 1 aborts for some reason, and then none of those updates should actually happen. So in order to make those updates take effect for all the other users in the database, in order to publish those changes, so to speak, the command that user number 1 has to run, that is a commit. And now the transaction has committed. So user number 1, of course, can still see those changes. But what has changed is that user number 2 now can also see those changes. And what you have seen here is an example of isolation, because as long as the transaction of user number 1 was not committed, only user number 1 was able to see the changes, while user number 2 did not see the changes yet. All right, so this is one simple example where we use isolation in the Postgres database system. Now let me quickly switch to my slides. And there's already some questions in the chat about how we can actually achieve those guarantees. We are going to discuss about that in a minute. So the operations in different transactions in general don't have to be commutative. All right. So in the following, we're going to discuss in more detail about isolation and about algorithms by which we can achieve isolation. Now, here we are again talking about the transaction manager. Specifically for isolation, the most relevant chapter in Ramakrishna and Gerke, that is chapter number 19. And as I have already explained, isolation is generally about simulating sequential execution to the users. Okay. Need to move something here. All right. Now, first of all, let's discuss in a little bit more detail about why we don't want to execute one transaction after another one. And there is at least two motivations. The first one being very long-running transactions. I mean, transactions like transferring a certain dollar amount from one account to another one, they are typically very fast to execute. But you could also imagine having some transactions that do very complex analysis on your database, and executing those transactions can actually take a long time. And if you imagine that we are executing all transactions one after the other one serially, then if you as a user submit one of those very short running transactions, however, your transactions gets scheduled after one of those very long running transactions. In that case, you as a user would have to wait for a long time until your transaction processes, even though your transaction is actually very short and inexpensive. So what is better here is to rather alternate between steps from different transactions, which means that the long transaction might be a tiny little bit slower because we interleave a couple of steps from the short running transaction, but the short running transaction will be as quick as one should expect. And that is why doing like interleaving steps from different transactions seems like a good idea in this scenario. Also, every once in a while, transactions might have to wait for data before executing the next step. For instance, if your data is mainly located on hard disk, then you might have to wait until we load that data from hard disk into main memory. And when waiting for data, then of course there's the choice that we just keep idle until the data arrives, but that wastes time. So it is better to rather schedule a step by a different transaction, which can already proceed because the data it needs is already in main memory. And then once that step from the other transaction finishes, maybe at that point data has been loaded, so the first transaction can make progress again. So for at least those two reasons, that people are interested in interleaving steps from different transactions. Now in the following, we're gonna discuss a lot about how we can interleave steps from different transactions to make sure that nothing bad happens. And in order to keep the examples we will see concise, we will use a short notation that is introduced on this slide. So this is important. You need to memorize the short notation because we will keep using it in all of the following examples. All right. So generally in that short notation, we describe read and write operations by transactions on database objects. So for the database objects, we typically use letters like A, B, C. And in order to distinguish different transactions, we use numbers. So that is typically represented as T1, T2, and so on. In order to represent operations by those transactions, we use R to abbreviate reads, W for abbreviating writes, and RW for abbreviating a combination of a read and a write. So for instance, if you write R1 of A, that means the transaction number 1 reads object A. We also use a C for commits and A for aborts. So if you write, for instance, C2, it means that transaction number 2 wants to commit. Now, let's make a little example with transactions, again, from the banking domain. And here we have pretty much the transaction that we have seen in our little demo. Here we are transferring $50 from the account of Bob to the account of Alice. And as we have seen, this requires 2 steps where we update the amounts in both of those accounts. Now, let's use a second transaction, which, for instance, adds the yearly interest rate. So here, let's say that we're adding 10%, and we need to add that for both of those accounts. So in principle, you could do this by one single query, of course, but here for the sake of the example, let's say that we do this for different accounts separately. All right. And if those 2 transactions execute at the same time, there's different possibilities about how we can interleave the steps of those transactions. So here there's a first possibility. We could, for instance, start with the first operation of the second transaction, and then do the first transaction, and finally do the second operation of the second transaction again. Second transaction in green, first transaction in blue. Now here on the left-hand side, you see the more verbose queries. On the right-hand side, you see the shorthand annotation. So here, for instance, at the beginning, we are updating the account of Bob, which means that we first of all read the current amount, and then we write an updated account after adding 10%. And that is represented by this RW for read write. 2 is the transaction ID, and B is the database object that we are writing on. So in this case, the database objects we are talking about, those are specific rows in a table. And here by B, we mean the row that is associated with Bob, and by A, we mean the row that is associated with Alice. All right. So this is one possibility of interleaving the operations of different transactions. Now, first of all, if we do this, if we interleave the operations in that way, do we have isolation? So will what we get be consistent with executing one transaction after another one? Or is that perhaps something that, do we see any effects that we would not see when executing one transaction after the other one? If anyone has an idea. Okay, somebody mentions data dependency issues. Yes, yes. Can anyone perhaps make a guess about what changes compared to executing one transaction after another one? If you think, for instance, about the final state of the database. Okay, okay, very good. All right, yes. Very good. And here I see a suggestion that the amounts in the account might be higher than they should be. Yes. Okay, very good. All right. So this is the, exactly, this is the right direction. So if we play it through in more detail. So if we execute one transaction after the other one, there's really only 2 possibilities here because you only have 2 transactions. So either we execute the first transaction first and then the second transaction, or we execute the second transaction, transaction number 2 first, and then transaction number 1. And here we have tried that, both possibilities. So if we first execute the transfer, and then the bonus. After doing that, Bob should have a $55 because the transfer was from Bob to Alice. Initially, we assume that both of them have, for instance, $100. And if you first transfer $50 from Bob to Alice, then Bob has $50 left. And if we add 10% afterwards, then Bob has $55. Alice, on the other side, since we do the transfer first, she has $150, and then 10% bonus makes $165. So if we first execute a transfer, then the bonus, then this is the amount of dollars that we should find in the end. Now, on the other side, if we first execute the bonus transaction and afterwards the transfer. Now, if both of them have $100, then after the bonus, both of them have $110 because we're adding 10%. And after that, we are transferring $50 from Bob to Alice. So Bob is left with $60, while Alice will receive $160. So those are the two possibilities. There's no more possibilities with two transactions. I only have the choice between which one of them I execute first. And as we see, both of those possibilities, they lead to a different final state in the database compared to the schedule that we have seen. Let me quickly remind you how that looks like. So here, first of all, we are adding the bonus for Bob. So if Bob has initially $100, then Bob will afterwards have $110. Now we are reducing the account of Bob by $50, so from 110 to 60, while for Alice, we increase from 100 to 150. And now we are adding still a bonus for Alice, which means that we have 165 for Alice. So in the end, we end up with $60 for Bob and $165 for Alice. And this final state is not achievable with any of the serial executions. Here, of course, in a certain way, you say both of them actually have more money than they should have. So from their perspective, it's a good outcome. But the bank, of course, controls the database server. And from the bank's perspective, it's not a good outcome. All right. And in any case, having this essentially destroys the illusion that your transactions execute serially that we want to give to the users. All right. Now, generally, whenever we destroy the illusion of serial execution towards the users, we call that an isolation anomaly. And in the forum, we're going to see a couple of different types of isolation anomalies. In particular, we're going to have a closer look at dirty reads, unrepeatable reads, and lost updates. So dirty reads, short description, essentially means we read data from a transaction that has only partially finished. Unrepeatable reads means we're reading data once, and then another transaction comes and changes that data. And once we read the data a second time in the same transaction, suddenly it has changed. And that also destroys the illusion of being the only one executing in the system at the same time. Also, lost updates means that different transactions essentially override the changes of other uncommitted transactions in a bad way. So all of those things can lead to problems and destroy the illusion of executing alone in the database. Following, we're going to discuss those different anomalies in a little bit more detail. All right, so first of all, we are going to discuss a little bit more about dirty reads. And that generally means that we read data from an uncommitted transaction. So if we read data from another transaction, it means that we might be influenced in what we do next by the values that we have read. And if you read data from uncommitted transactions, it's actually very risky because we never know whether that other transaction might actually finally commit or whether it might finally abort. Because if the transaction aborts, then I have read values and acted upon them, which are actually invalid because the database should, in the end, look as if aborted transactions have never happened. So if I read values from those uncommitted transactions and get influenced by those values, it might indirectly reflect effects caused by those transactions that might later abort, which is invalid. Even if I read data from another transaction that might finally commit, that still might lead to strange effects. So generally, dirty reads is something to avoid. And in the demo that we have seen before, for instance, you've seen that when user number 1 was updating the database, then user number 2 did still not see those updates before the transaction has committed. So this is what we are trying to do there. The database system is trying to avoid dirty reads. So user number 2 cannot yet see the uncommitted changes from user number 1. And once we think about the shorthand notation that we have introduced, then the general signature, so to speak, from those dirty reads, that is a write by some first transaction X on object A, followed by a read by another transaction, but on the same object, without any commit between those two operations. So the first transaction X has not yet committed, and still transaction Y is already reading its values. Unrepeatable reads means essentially that the data you are working on keeps changing without you being the one changing it. So that is very clearly destroying the illusion of being the only one executing transactions at the same time. So in general, an unrepeatable read means that we read the same data twice without changing it, but still suddenly the data changes, which means there must be somebody else changing the same data concurrently with me. For instance, one situation in which that can cause a problem, let's say that we are talking about the database of an online shop, and that database essentially takes in orders from customers. So before accepting an order, it needs to check whether it still has enough items in store in order to satisfy the order. So we could imagine that we check the number of items once, and we see, oh, we still have an item left, and then we do something else. But in the meantime, a different transaction, perhaps a different order, comes in and reduces the item count that I'm currently working with. And now once I try to finish the order and want to reduce the item count further, maybe the other transaction has already reduced it to 0. So now I'm trying to subtract 1 and make it negative, which probably is not permitted by the database. So at that point, I'm creating problems, and I might end up with an inconsistent database. So that is one situation in which those unrepeatable reads can create problems, but that's just one example. And the general signature of those unrepeatable reads is that one transaction X reads an object A, then another transaction comes along and changes the value of object A and commits. So even if I don't have a dirty read, then that value has changed. And now the first transaction X again reads the same object and now suddenly finds that it has changed. So that is another anomaly that we want to avoid. One more is lost updates. And that essentially means that different transactions override each other's values while they are executing. And that can create problems because it can lead to an inconsistent database state. For instance, let's say that you want to keep the salary of all employees in a certain department the same for fairness. So you have multiple transactions that update the salary. And if two of those transactions interleave their operations, it might be possible that some of the employees get salary 1, while some other employees get salary 2, which is something that you want to avoid. And you could avoid that if executing transactions one after the other one, because then it would be guaranteed that all employees always get assigned to the same salary. And that problem is generally called the lost update problem, because the updates from some transactions, they might get overridden by other transactions and without committing before. And the signature of that anomaly is the one that you see here. That's simply like one transaction X writes a value to an object A, and then before that transaction commits, another transaction Y comes along and simply overwrites the value on the same object. That is the lost update problem. One more problem, one more anomaly that we will discuss a little bit more about later in the course, that is the so-called phantom problem. So I'm already mentioning it here anyway. That is kind of like an extension of the unrepeatable read, but in the context of insertions. And that is something such as, for instance, retrieving all the students whose name starts with a certain letter, all right? And doing that twice within the same transaction. Now it might happen that when running the query the second time, suddenly more students appear in the result. And that can happen if a different transaction has inserted students between the first query and the second query. And that is also something which destroys the illusion of isolation. And therefore, we want to avoid it. So we are going to discuss this later in more detail, not now, because it essentially requires some extension of the notation. So far, in our notation, we assume that we update database objects that exist already. Like we are updating, we are reading, and we are writing objects A, B, and C, and so on. Here, what we are doing is that we are essentially inserting new objects after a query has executed the first time and before it executes the second time. And for that reason, we're going to discuss that in more detail later, and we are going to first focus on the first three anomalies. All right. Now, in the SQL standard, you actually have different isolation levels. So that means that for certain applications, it might be acceptable to have some of those anomalies, but not others. Isolation can be very expensive performance-wise. So that means that sometimes you might be willing to accept even some slightly strange behavior of your database if in exchange your database can process transactions much faster. And this is why SQL gives you the choice between different isolation levels. So here on the left column, you have the different isolation levels. Read uncommitted, which allows essentially anything. Read committed, which already avoids a dirty read because we are only allowed to read data from committed transactions. Repeatable reads, which avoids the unrepeatable read anomaly. And finally, generalizable, which means that here we have a nearly perfect illusion of isolation. So here on the column on the left, you see the different isolation levels, and the top row is associated with those different anomalies. And you see for each isolation level whether the corresponding anomaly may appear or not. This is how you can change those things in Postgres. In Postgres, you can, for instance, set a default isolation level with the set session characteristics command. You can also set specific isolation levels for specific transactions, because perhaps you have some transactions that are more critical than other transactions. So you can set higher isolation levels for the more critical transactions. You can use that by writing something like set transaction isolation level serializable, for instance. And then this current transaction would be assigned to that isolation level. One thing to know is that many people think by default the database system might support the highest isolation level, but that is often not the case, and that can sometimes lead to problems. So for instance, in Postgres, the default would be a read committed. So one of the a little bit weaker isolation levels actually. So some of those anomalies might appear. You can manually set that isolation level higher. And depending on what kind of application you're working on, I would recommend you to do that. So make sure when using a database system that you're well aware of which isolation level you need and which isolation level your database system is currently using. All right. Now in the following, we're going to discuss more in particular about the serializable isolation level, and we're going to discuss about protocols by which we can guarantee that. We won't have too much time to start with that anymore today, but I already give you a little teaser of what we will be doing. We will generally talk more about concurrency control, which is the process by which we achieve isolation, basically. So how that looks like is that you typically have a component somewhere in a database system which performs concurrency control. So the input to that component are the transactions, and the output of that component is a schedule, meaning an order between steps of different transactions that might interleave the steps of different transactions. And then the goal of concurrency control is to select the schedule that is cheapest to execute while still avoiding all of those anomalies that we have seen before. All right, so we're gonna discuss more about this the next time. Let me quickly see, I think there's some questions in the chat. Okay, very good question. So the question is, why would ever want to use a weaker isolation level than serializable if it means that the data in my database can, that there can be anomalies generally? So it depends on what data you are storing and what transactions you're executing on it. For instance, if you have something like, for instance, you have an online shop which has some kind of a visit counter for the website, which is also maintained in the database. Now, if the number of visits is a little bit off to what you would actually expect, it might not be the end of the world. I mean, if you can get significantly better performance and your visit counter of the website might be a little bit off, you would probably accept it. Now, on the other side, when it comes to things like orders, when it comes to updating your inventory list, then those are things that are highly critical where you want to avoid any strange behavior. So that is why SQL allows you to set the isolation level for specific transactions, so you can distinguish the ones that are more important from the ones where a little bit of strange behavior might be acceptable. So it depends entirely on your application. But there is situations in which you probably want to accept a lower isolation level than serializable. Is at this point any other questions on transactions? All right, okay. And there's one question about the difference between dirty and unrepeatable read. And that is a well-justified question because there's some similarity between those two. I mean, in both cases, we are reading something that we shouldn't really read. Now, the thing is this. For dirty read, it means specifically we are reading values from an uncommitted transaction. That means between another transaction writes a value and I'm reading the value, there's no commit by the other transaction in between. Now, for an unrepeatable read, the second read might actually read some values from a transaction that has already committed. So that means the transaction I'm reading from cannot abort anymore, but nevertheless, it is an anomaly because I have already read the same value before in the same transaction, and now I see that those two values differ. So the difference between the two is really on whether I'm reading committed or potentially uncommitted values. In case of unrepeatable read, I might read a committed value, which however differs from another committed value that I have read previously in the same transaction. And there is some question about whether people could maybe exploit those lower isolation levels in order to increase the visitor count. That depends a lot on how your data looks like and how your transactions look like. I mean, in general, the visitor count, I use that as an example for something where you might be willing to accept the values that deviate from the real values. Perhaps in practice, if you see that your visit count seems to deviate by a lot from what you are actually expecting, then you might decide to also make that transaction serializable, the one that is updating the visitor count. But probably it's a piece of your database that is less critical than others. All right, good. So that was an introduction to transactions. And we have started discussing about isolation. In the following lectures, we will discuss in more detail about isolation and about methods by which we can achieve isolation. Have a nice day, and I see you again on Wednesday.